Hi Year 12, welcome to the next videos here on logarithmic functions. We have looked at integrating reciprocal functions where the numerator is either the differential of the denominator or something pretty close to it. We just want to look at applications of that now. So we're looking at things like tangents and normals and, in fact not so much tangents and normals. No, we're going to be looking at things like areas and volumes, right? Because that's the applications of integration. Tangents and normals, that sort of stuff, are applications of differentiation. So, first of all, first example here, we've got a hyperbola, right, which I can rewrite as y equals 2 over x, which is a reciprocal function, and this straight line. Now, first thing I've got to show that they intersect at these points. We could solve these two things simultaneously. We get a quadratic. We're going to get solutions for x at x equals 1 and 2. Then I substitute those in and find that y corresponds to 2 and 1. Or, right, because I've already been given them, I can easily substitute in. So I'm going to say sub 1, 2. And I get xy equals 1 by 2 equals 2. And I also get x plus y equals 1 plus 2 equals 3. Great. Sub 2, 1. I get the same thing. xy equals 2 by 1 equals 2, and x plus y equals 2 plus 1 equals 3, right? And that'll do, I think, to show that they intersect at those places. Sketch the situation. Right, well, I have here's my axis, x and y. My rectangular hyperbola, xy equals 2. Does this sort of thing, and this sort of thing, right, with asymptotes as the axes, and then x plus y equals 3, or if you prefer, y equals negative x plus 3, right, that does this sort of thing. Crosses here at 3, crosses here at 3, crosses here at 1, 2, and here at 2, 1. There you go, there's the situation. Maybe not to scale, but you know, it's alright. It's alright. Find the area of the region between the two curves. So now, I am after, oh, can I do something here? Oh, what happened there? Oh, here we go, try this. Oh, let's try a different colour. I'm after this region in here, aren't I? Right, I'm after that region there, which means that I am after the integral from x equals 1 to 2. So my area, equals the integral. Oh, why is this going all weird on me? From 1 to 2. Oh, something weird has happened. The integral from 1 to 2. That's not right. Hang on. Sorry, I'm back after some minor technical difficulties. So my area is equal to the integral from 1 to 2 of, right, I want to write this as y equals negative x plus 3, of negative x plus 3. It's my line minus this other one, which is 2 over x dx. Okay, so it's the integral of the top line minus the bottom line dx between 1 and 2. And it's going to give me the area between them. So, this part here is fine, negative x. This part here, the 3, that's fine. Negative 2 over x, that's not too bad. It's a reciprocal function. So this equals negative x is negative half x squared plus 3x. Now just think of this as negative 2 instead of 1 of x. So it's minus 2 log x from 1 to 2. And I just need to substitute in here now. So first of all, the 2 goes in. I get 2 squared is 4. Half of 4 is 2, negative 2. So I get negative 2. I get plus 6. Right, minus 2 log 2. I can't simplify that very much. 2. You'll see I still prefer the ln just because it's faster, I suppose. Now, minus, subtract the 1s off this. 1 squared is 1, negative half. So that's plus a half. Now, I've got to subtract 3 lots 1. Minus 3. Log of 1 is 0. Okay, so I don't have to worry about that log 2. I can tidy up some like terms here. I could just say minus 0. Some like terms. 6 minus 2 is 4. Minus 3 is 1 plus a half. Oh, 1 and a half. I'm going to say it's 3 over 2, because it's nicer than 1 and a half, minus 2 log 2. And I reckon that's the answer. Okay, that comes out fairly neatly. That's the area between those two curves. Rightio, so that's one way of applying the integration of reciprocal functions. Another one here is we can use volumes. Now remember, volume rotated about the x-axis is pi y squared dx. Righto. Now, rotating about the y-axis, it's pi times the integral, of x squared dy. Okay, so we know that y equals 1 over x squared. Therefore, x squared equals 1 over y. So my volume, now I need my bounds to be on the y-axis. That's fine, they're already given to us as the y values. I don't have to substitute those in find to sort of switch them over. Volume equals pi, pi times the integral from 1 to 2 of x squared dy, right, because it's around the y-axis, equals pi times the integral from 1 to 2 of 1 over y dy equals, now the integral of 1 over y is the log of y. So we get, stop erasing my writing, pi times the log, natural log of y from 1 to 2 equals, we're just about done here, so I get equals pi times the log of 2 minus the log of 1, which is 0, so I just get pi log 2 cubic units. I should come back up here, don't forget units, square units there. Rightio, that's our volume. Rightio, and that's it for applications. We're going to look at change of base next, but that'll do us for today. That'll get us through the week, you know. Okay, see you next time.